we have a crisis of confidence in elections in the US today. We have millions of voters who simply do not believe the results of recent elections. And this is not just in the US. Brazil followed a path very similar to the US almost exactly 2 years later. And there are many millions more people in otherwise well-functioning democracies around the world who for various reasons do not believe the results of their elections. Now, regardless of how you view these opinions, there are some objective truths that we have to acknowledge. And it begins with the fact that we are doing a very poor job of giving voters any direct substantive evidence that their votes have been accurately counted. We instead are asking voters to simply check what their local election officials have said and believe their local election officials rather than giving them anything more substantial than that. And because of that, an election in the US or Canada or Brazil or Western Europe, from a voter's perspective, looks pretty much the same as an election in Iran or Russia or perhaps Venezuela. We're really not giving voters the tools that they need. There is an approach that directly addresses this. There's a technology that started over 40 years ago and has evolved since then, called end-to-end verifiability, which directly addresses this. It allows voters to check that their votes have been accurately recorded, and it allows anyone to verify that the recorded votes have been accurately tallied. Okay? This really does get right at the essence of the problems we have. And this is possible without asking voters or anyone to trust anything at all. They can do this without having to trust election officials, hardware, software. They can check everything for themselves. And it works against not just known attacks, but any possible attack that may not have been thought up. Insider attacks, outsider attacks. It's a very powerful technology. In the time that this has gone on, there have been hundreds of research papers written about this technology. There have been expert reports from a variety of sources. There have been standards written in the US by the Election Assistance Commission, by the Council of Europe. There's a lot of reason to support this, and there have been many, many designs for these verifiable election systems. Many of these designs have been implemented and used for student elections, and usually very little more. There are a few that have been used for internet voting. And there's at least one, maybe more depending on how you count, that's been used in in-person public elections, which I think is really the critical place here that we have to concentrate. But that was very small, few hundred voters, not very big. So why am I here? This has been done, and it's been done, and it's been done, and it's been done, and I'm doing it again. We have decided that this approach isn't working, in large part because we're trying to fight the existing infrastructure and say, here's this much better way of doing it. You should do it this way instead. Come on, please do it this way. Forget what's already there. And it's very hard to just replace this existing infrastructure. So instead, we did not build an election system like everybody has in the past. What we've done is built tools, free, open source, MIT licensed tools that can be used within the existing infrastructure by the existing vendors and entities. Tools that run alongside of instead of replacing the existing infrastructure so that the existing counts can still be maintained. We're just providing a verifiable auxiliary count. What we're doing is saying and recognizing that the existing established vendor community doesn't have the resources, they don't have the cryptographic expertise to build the zero-knowledge proofs, the homomorphic encryption, the other things that have to go in there. We've built all that, and it just, it's a toolkit that can be used. So what does this look like? Well, it turns out that the API to develop this is really surprisingly simple and very flexible. All that has to happen is anytime a vote is collected, and collected on whatever device is being used, it works on a variety of devices, a touch screen, optical scanners, can even work with vote by mail, although it has to be done differently in that case. Every time a vote is collected, ElectionGuard is called, ElectionGuard does the appropriate encryption, the zero-knowledge proofs and whatnot, returns a confirmation code to be given to the voter. That's the only interaction with the existing infrastructure. Now, the voters can take these confirmation codes, which do not say how they voted. I have to say that as clearly as possible. It does not allow them to show anybody else how they voted. Think of it like a tracking code. But they can take this code, and that's sort of their entry into the system to figure out and see that their vote is accurately counted. But we recognize most voters aren't going to do this. That's okay. Most voters can crumble this up and throw it away. Most voters just want to vote and be done with it. That's fine. But anybody who is concerned has a means of checking and being confident in the result. So there are a lot of choices to be made in exactly what tools to build, because there have been, as I say, hundreds of papers on this. So the guiding principle that we used here is that verification should be as easy as we can possibly make it. We're doing a lot of work, we're the experts. We want the integrity of an election to be verifiable by a first-year programming student. We want it to be as simple as possible, and we're willing to do extra work to make that possible. So, first thing there is, I keep getting asked, why don't you use elliptic curves? That's the newer thing, right? They're more efficient. Try getting a first-year student to use elliptic curves versus integers, and you'll see the problem. We're doing a simple integer groups, things become much, much easier. We've actually been able to get things down to just 4 operations that are required to verify an entire election. Modular addition, modular multiplication, not even modular division, because that's tougher. When a division is required, we'll do the division and you just have to verify the multiplication is correct. Modular exponentiation, of course, and hash computations. What's the hardest of these to get right? It surprised me as a cryptographer thinking, oh, the hash functions, that's the easy part. Just throw everything in, just make sure it's unambiguous, you're done. Hash functions by far were the biggest headache when we first deployed this and I started working with students and whatnot. So we've since put in a lot of time and effort to make the hashing very clear, very unambiguous, very well specified, so it's much, much easier now, so that problem is mostly gone. It's certainly a lot easier. Other big pain point we found in our early deployments here is the trustee process. Like with many, many cryptographic protocols, we divide the trust amongst many entities. We use threshold encryption, so there isn't one single entity that has a key that can read all of the votes. Everything works great, the mathematics is beautiful on this. But for verifiers, trying to deal with, well, you had all the trustees, or no, one was missing, which one was missing? Okay, now I've got to figure out Lagrange coefficients once I figure out which set I have and whatnot. That turned out to be quite a pain. So we were able to figure out how to algebraically combine all these individual separate trustee proofs of correct decryptions into single decryption proofs. So from the point of view of verifier, this isn't a threshold encryption. This is just a single encryption, and they're verifying a single decryption. Again, much simpler, much cleaner. Okay? So we have used this in many places so far. The left column is the things that I'm most interested in because in-person, as I said, is really where I want to target this. We've worked with multiple vendors. I'll mention the second example on this list is an audit, an RLA, very much like we heard about in the last talk, where we used ElectionGuard to preserve the privacy of individual voters in a post-election audit, again showing the flexibility of these tools. But there are a lot of other cases. The top one in the right column is interesting. We were actually used in the US House Democratic Caucus in their leadership elections in 2020 because they were remote. Because of COVID, they wanted to find a way to have a verifiable election remotely, and we were able to work with them. And there have, again, been many other cases where this has been used. So where are things? Well, we've got now a very stable design. Our v2.1 specification has just been released. Very detailed, very stable, very, very happy with it. We've got a draft data specification for the formatting, because if you're going to write a verifier, it's not good enough to just look at the code and see exactly how the data is structured. Unfortunately, it's still in draft form. We hope to have it up to perfect v2.1 in a couple of weeks. You can look for all these things at our electionguard.vote website. We have implementations in various languages. This was originated and built in Microsoft, but Microsoft recognized early on that if this is going to be widely deployed, it can't be managed and controlled by Microsoft. So we're working with a new entity as a nonprofit called the Election Technology Initiative. They now have management control over ElectionGuard, but it's all open source. Anybody can use it without asking me. In fact, just last week I learned of a new company that's using it that I didn't know about before. In the future, we're hoping for more, bigger deployments. We want to expand the use cases, build a mixed-net version for ranked choice voting, verifiable write-ins, other use cases. We want to continue some of the research on optimization. There's some good opportunities for using snarks. The thing we did with the combining the threshold encryption is a little snark-like, but there may be good opportunities to use snarks to make verification more efficient, because it's now easy, but it's a little slow. And the big thing is we want to broaden our network of the vendors using this, the people writing verifiers. I want this to be an exercise in a first-year programming class. Here it is, everybody write a verifier. I have thousands of them out there. We welcome contributors, reviewers of the design, anything. Here are some obligatory references, including in particular, go to electionguard.vote and you'll find pointers to everything you need, and plus the reports and some not the specifications, the standards that have been written on this. And I'm happy to take any questions that you might have.